the top of the waveform. It's the highest amplitude from the middle of its greatest width. And so just the highest amplitude of the waveform is the peak. And the trough is the opposite, it's the lowest. And the baseline is the moment that it crosses zero. And that is everything. Deflection is when it changes from zero. Peak is the highest point, trough is the lowest. And baseline is the moment that something crosses zero. It's all measured in microvolts. And standard EEG in an adult ranges from 0 to maybe sometimes 20 microvolts. And eye blink is 70 microvolts to give you an idea of the change in the size. I often measure signals from 1 to 2 microvolts, but 7 is a real standard, what we expect to see in an ongoing EEG. And so we're talking itsy bitsy. That's what a microvolt is. That's the unit of the microvolt is the itsy bitsy. Yes?
Isn't the resting potential for a neuron 20 microvolts? Isn't it like the threshold level for a neuron to fire?
Is it 20?
I thought it was 20.
You should be convinced about that statement.
Can you Google it?
Yeah, that's it. But I know where you're going with that. The difference is that we're measuring on the surface of the head,
Okay.
and we're not measuring the firing potential.
Okay.
We're measuring what's received by the other neurons. What's received after it fires, so what's received in the dendrites. It takes about 15 million of these guys to fire all at once for us to be able to see it on the surface of the scalp. So 15 million, so long story short, you don't see anything till you get to layer 3 or 4 on its way out of the system, because everything has to summate.
It's actually negative 60 and negative 70 is the resting potential of a neuron. So 28 I think is the membrane potential.
Well done. Individual channel recordings. Each electrode produces a recording over time. I have 40 out of my 128. And so let's look at channel 38 here. We're going across time. We're going across, okay, we're going across a lot of time. How much time are we going across? 5 millimeters per second. A lot of time. And the individual channels up and down. See this right here? They blinked. And then here, they blinked. And then after they blinked, they went, did this thing. They're like, ah. And so that's what this little thing is here. Now you might notice, because you guys are pretty far away, that there are these points here. See these?
Mm-hmm.
If I were to magnify you for those stupid things are heartbeats that I allowed to get into this signal. In other words, I'm not showing you perhaps the best EEG I should have for this demonstration. Yes.
There's one kind of close to the bottom.
This guy.
Yeah, what's going on there?
So this one does not have good contact with the scalp. And so what Catherine was talking about there a second ago about electrodes having a new system, we're always trying to find better ways to have good contact with the scalp. This system uses sponges filled with a salt water-like solution, potassium chloride, and literally what happened here is this one dried out. But I don't care, I've got 128. How do we identify an exact waveform in EEG? Now, we're going to stand for ERPs too. EEG is the resting ongoing state for the purposes of this class. ERPs are responses to stimuli. There is a special way that we can measure EEGs that allow us to know whether it's a response to a stimuli coming in, but we're going to divide an EEG ongoing state versus ERP, a response to something. ERP is electroencephalographic waveform, and ERP is evoked potential or event-related potential. Time, at what frequency does the waveform occur? Alpha, 8 to 10, beta, well, 8 to 12, beta, 13 to 30, gamma, 40 hertz, delta, 2 to 4 hertz, theta, 4 to 8 hertz, and then you can break it down to subbands. We're not going to do that. Space, the topography of the waveform. Where is it? Here. If you see a mass of alpha coming from the back of the head while somebody has their eyes closed, that's just fine. If you see the highest potential of alpha coming from the frontal lobes while somebody has their eyes closed, something's wrong. Something is very, very wrong. Where it's coming from the surface of the head is extremely important to define each of these. Another way we can do this is we can localize the region of the brain that produced the waveform. I'll show you how that's done. Comes back to dipole source localization. And it's the kind of math that psychologists love because there's an infinite number of possible solutions. And so we can't be wrong. I solved this equation, you must be right. There are ways we can refine our solutions. Very important, the context, the experimental, and this is for me, the mental events that are happening at the time that the person is experiencing the waveforms. I'm going to give you a great example. In my studies at the beginning of the semester, I see people with alpha and some theta and lots of beta. At the end of the semester, you've got papers due, you're working, you're up all the time. People come into my lab, they will have their eyes open, they will tell me they're perfectly fine. And they're into the study and somehow they're still responding. I don't know how they're doing it. And I am registering delta. That's a waveform associated with deep sleep. And so that tells me a lot about context, and it's very regular. It's a phenomenon I've observed for many years. And so the context of what's going on, if you see delta in somebody on a normal circumstance and they're alert and they're awake and they're focused, there's something damaged in their cortex. However, if you pushed yourself beyond the state of exhaustion, your brain will try to go to sleep. Your brain will go, and you need some sleep now. We need to sleep.
That'd be interesting to like do, I'm sorry.
No, go ahead.
But that'd be really interesting to do like EEG on like infantry soldiers who spend like an entire week and only get about 4 hours of sleep throughout the week.
They do studies like that at Aberdeen. What we do know, and there's a whole branch of the military that does sleep research, we do know you can't push it beyond 96 hours no matter what you do. And at 96 hours, you need to give them some sort of medication in order to keep them awake, but they'll still have what are called microsleeps. They'll be standing and then suddenly just be asleep. And it will start to be uncontrollable over time. There's a great study called the Human Lab over in England. And in England, for fun, they kind of do public experiments and in the Human Lab. And so they brought people in and had them stay awake. And as they got longer, closer to the 96-hour limit, people had to watch them every second because they could go from alert and just fall down because it was time to sleep. And so you can't really push that envelope. The military has tried. Yes?
Do people with like narcolepsy, do they have more delta waves like on a typical basis, or?
That's a really good question. The answer to that question is I don't know. I believe that, well, there's a very strong genetic component to narcolepsy, and I don't know what's going on there. I think that you're looking at more an unlocking of the interconnectedness of brain regions and consciousness from other things, which is involved through sleep spindles and K complexes, like that stage 2 sleep kind of thing. But you might be right. I'm just conjecture. I don't know.